Here you are, floating somewhere between the waking world and the gentle pull of sleep, perhaps scrolling through your phone or settling into bed with that familiar glow of curiosity that draws us to the mysteries of the universe. Tonight's quiet journey takes us to a place where the very fabric of reality bends and whispers secrets that have puzzled the greatest minds for over a century. We're going to explore an experiment so simple a child could perform it, yet so profound it changes everything we think we know about existence itself. Before we slip into this scientific reverie, I'd love to know where in the world you're resting tonight, what time it is in your corner of the cosmos, and whether you've ever wondered if the act of simply looking at something could change what it actually is. Quite fitting, isn't it, that we're all here observing this very moment together, each of us perhaps changing something fundamental about reality just by being present. If you find this gentle exploration soothing, intriguing, or simply a nice way to drift toward understanding while your mind prepares for rest, I'd be ever so grateful if you gave this video a like. It helps this quiet corner of science reach others who might need a peaceful pause from the chaos of certainty. Now, I do hope this isn't so mind-bending that it keeps you awake, but if it does, at least you'll have glimpsed one of the universe's most beautiful paradoxes before you drift off. So settle in, let your thoughts slow like settling dust, and prepare yourself for a story that begins with two simple slits in a piece of material and ends with questions that have no comfortable answers. Because somewhere between light and shadow, between particle and wave, between the seen and unseen lies an experiment that suggests reality itself might be far stranger and more intimate than we ever dared imagine. Picture, if you will, a darkened room. Not the dramatic darkness of a theatre, but the gentle dimness of a space where precision matters more than spectacle. In this room sits an apparatus so elegantly simple it could have been built centuries ago, yet so revolutionary in its implications that it continues to unravel our understanding of existence today. Two parallel slits, no wider than a hair, carved into an opaque barrier. Behind them, a screen waiting to catch whatever passes through, and in front, a source of light so faint it releases photons one by one, like gentle raindrops in the softest drizzle. This is the double-slit experiment, and if you've never encountered it before, prepare yourself for a journey that will leave you questioning the very nature of what we call real. If you have heard of it, settle in anyway, because tonight we're taking the scenic route through its mysteries, letting each strange revelation unfold like a meditation on the impossible. The story begins innocently enough, as most profound discoveries do. In 1801, a British polymath named Thomas Young was investigating the nature of light. Was it made of particles, tiny bullets of energy shooting through space? Or was it a wave, rippling through some invisible medium like sound through air? Young devised an experiment of such elegant simplicity that it would echo through the centuries, growing more mysterious with each retelling. He took a barrier, made two narrow slits in it, and shone light through both slits onto a screen behind. What he saw defied the particle theory of light completely. Instead of two bright lines corresponding to the two slits, the screen showed an interference pattern, alternating bands of light and dark, like the ripples you might see when two stones are dropped simultaneously into a still pond. Where the waves met in harmony, they created brightness. Where they cancelled each other out, darkness bloomed. Light, Young concluded, must be a wave. The two slits were creating two separate wave sources, and these waves were interfering with each other, creating that beautiful striped pattern. It was elegant, it was logical, and it seemed to settle the question once and for all. Light was a wave, not a particle, and the universe made sense. But the universe, as we would discover, is not particularly interested in making sense. For over a century, Young's wave theory of light reigned supreme. Scientists built their understanding of optics, of radiation, of the electromagnetic spectrum on this foundation. Light was a wave, and waves behaved in predictable, comprehensible ways. They could interfere with each other, They could be bent and focused, they could spread out and diffract around obstacles. The mathematics was beautiful, the predictions were accurate, and the world seemed orderly. Then came the early 20th century, and with it, a series of discoveries that would shatter this comfortable certainty. Max Planck, investigating the way hot objects radiate energy, found that energy came in discrete packets, little bundles he called quanta. Albert Einstein, building on Planck's work, explained the photoelectric effect by proposing that light itself came in these packets, particles of energy he called photons. Suddenly, light was a particle again, and the wave theory seemed quaint and outdated. But here's where our story takes its first strange turn. Both theories worked. Light behaved like a wave when you looked for wave properties, and like a particle when you looked for particle properties. It was as if reality couldn't make up its mind, or perhaps more unsettling, as if reality depended on how you chose to look at it. This is where the double slit experiment transforms from a simple investigation into a profound meditation on the nature of existence. Because when scientists decided to fire individual photons through the double slit apparatus, one at a time, something extraordinary happened. Something that still makes physicists uncomfortable more than a century later. You might expect that firing photons one by one would eliminate the interference pattern. After all, a single photon can't interfere with itself, can it? It must go through one slit or the other like a marble rolling through one of two doorways. You'd expect to see two bright lines on the screen, one behind each slit, growing brighter as more photons accumulated over time. But that's not what happens. Even when photons are fired one at a time, even when there's no possible way for them to interact with each other, the interference pattern still emerges. Stripe by stripe, photon by photon, the same mysterious bands of light and dark appear on the screen. It's as if each individual photon somehow passes through both slits simultaneously, interfering with itself to create this pattern of possibility and prohibition. This is the heart of the mystery that has haunted physics for over a century. How can a single photon, a single particle of light, be in two places at once? How can it pass through both slits when common sense tells us it must choose one path or the other? The answer, according to quantum mechanics, is that the photon doesn't choose. It exists in what physicists call a superposition, a ghostly combination of all possible states until the moment it's detected. In the quantum realm, the photon is neither here nor there, but everywhere it could possibly be, weighted by probability. It's a cloud of potential, a whisper of possibility, a mathematical phantom that somehow produces very real effects. The interference pattern on the screen isn't created by photons bumping into each other. It's created by each photon interfering with all the places it could have been, all the paths it could have taken, all the possibilities that exist in the space between emission and detection. This might sound like abstract philosophy, but it's as real as the ground beneath your feet. The pattern emerges, photon by photon, each one landing in a location that contributes to the larger design. Where the pattern predicts brightness, photons are likely to arrive. Where it predicts darkness, they're forbidden from landing. It's as if the universe is consulting some hidden blueprint, some probability map that guides each photon to its destined location. But here's where our gentle journey into the quantum realm takes perhaps its most unsettling turn. Scientists, being curious creatures, decided to peek behind the curtain. They wanted to know which slit each photon actually passed through. Surely, they reasoned, if we can detect the photon at one slit or the other, we can solve this mystery of superposition once and for all. So they set up detectors at each slit, devices sensitive enough to register the passage of a single photon. Now they could watch the experiment unfold, observing each photon as it made its journey from source to screen. They could finally answer the question that had been haunting them. Which path does the photon actually take? The answer they got was more disturbing than any they could have imagined. When the detectors were in place, when the photons were being observed, the interference pattern vanished. Completely. Instead of the mysterious stripes of light and dark, the screen showed exactly what common sense predicted: two bright lines, one behind each slit. The photons behaved like ordinary particles, each one definitively passing through one slit or the other. No superposition, no quantum weirdness, just simple, predictable, classical physics. But turn off the detectors, stop observing which slit the photon passes through, and the interference pattern returns. The quantum mystery reasserts itself, and the photons go back to their impossible dance of being in multiple places at once. It's as if the universe is playing a cosmic game of hide and seek, revealing its secrets only when no one is looking. This is the observer effect, and it's perhaps the most profound and disturbing implication of quantum mechanics. The act of observation, of measurement, of simply looking to see what's happening, fundamentally changes what happens. Reality, it seems, is not independent of observation. The universe doesn't just exist in some fixed state waiting for us to discover it. But what happens when we add a detective to the slits? When we place a sensor, a quantum watchman, to observe which path each photon takes? The results are nothing short of bewildering. The moment we try to peek, the moment we attempt to catch the photon in the act of being a wave, something fundamental shifts. The interference pattern vanishes completely. Gone are the elegant zebra stripes of light and dark. Instead, we see exactly what our classical intuition would expect: two bright bands, one behind each slit, as if the photons are well-behaved particles that simply choose one path or the other. This is the observer effect in its most pristine form. The very act of measurement, of trying to determine which slit the photon passes through, fundamentally alters the nature of the photon itself. It's as if reality has two faces, and it shows us the one we're looking for. Search for a wave and you'll find wave-like behavior. Search for a particle, and particles you shall receive, but you cannot have both simultaneously. The implications ripple outward like stones dropped in still water. If the simple act of observation can change the behavior of light, what does this say about the nature of reality itself? Are we passive observers of a universe that exists independently of us, or are we active participants in its very creation? The double-slit experiment whispers that perhaps the universe is not a film we're watching, but a story we're helping to write moment by moment, measurement by measurement. Consider the peculiar timing of this collapse. The photon doesn't simply choose a path when it encounters our detector. According to quantum mechanics, it exists in a superposition of all possible paths until the moment of observation. Only then does it collapse into a single, definite reality. It's as if the universe is holding its breath, keeping all possibilities alive until someone bothers to look. This leads to even stranger questions. What constitutes an observation? Must it be a conscious human observer, or will any measuring device suffice? The answer, thankfully or perhaps disturbingly, is that consciousness itself doesn't seem to be required. Any interaction that could, in principle, reveal which path the photon took will cause the wave function to collapse. A simple photodetector, a grain of dust, even the faintest interaction with air molecules, all can serve as observers. The universe doesn't need our awareness to make its choices, but it does need some form of interaction, some exchange of information that pins down the photon's behavior. But here's where things become truly mind-bending. We can play games with this observer effect. We can set up delayed choice experiments, where we decide whether or not to observe the photon's path after it has already passed through the slits. Logic would suggest that the photon must have already decided whether to behave as a wave or a particle by the time it reaches the screen. Yet experiments show that our future choice of measurement still determines the photon's past behavior. It's as if information can flow backward through time, as if the universe is constantly revising its own history based on what we choose to observe. This isn't science fiction or philosophical speculation. These experiments have been performed countless times, with results that consistently defy our everyday understanding of cause and effect. The quantum world operates by rules that seem to mock our classical intuitions about how things should work. Particles can be in multiple states simultaneously. They can influence each other instantaneously across vast distances, and the future can somehow reach back to determine the past. The observer effect extends far beyond photons and slits. It appears in every quantum system, from electrons orbiting atoms to the spin of particles in magnetic fields. Everywhere we look in the quantum realm, we find the same unsettling truth. Reality is not fixed and definite until it is observed. The universe exists in a state of pure potential, a shimmering cloud of possibilities that crystallizes into concrete reality only when prodded by measurement. This has profound implications for our understanding of existence itself. If observation creates reality, then what exists when no one is watching? Does the moon exist when no one observes it? Einstein famously asked this question, and quantum mechanics suggests the answer might be more complex than we'd like. Perhaps the moon exists in a superposition of states, neither fully there nor fully absent, until someone looks up at the night sky. The observer effect also raises questions about the nature of time and causality. If the act of measurement can retroactively determine the past behavior of particles, what does this mean for our understanding of history? Are the events of the past fixed and immutable, or are they constantly being reshaped by present observations? The quantum world suggests that reality might be more fluid than we ever imagined. Some interpretations of quantum mechanics take this even further. The many worlds interpretation proposes that every quantum measurement doesn't collapse the wave function, but instead splits the universe into multiple branches, each representing a different possible outcome. In this view, the observer effect doesn't choose one reality over others. It determines which branch of the multiverse we happen to experience. Somewhere in another branch, the photon took a different path, and another version of you is reading about different results. But perhaps the most unsettling aspect of the observer effect is what it reveals about the relationship between mind and matter, between consciousness and cosmos. While consciousness itself may not be required for wave function collapse, the fact that our choices of measurement can influence reality suggests a deep connection between the observer and the observed. We are not separate from the universe we study. We are woven into its very fabric. This participatory nature of reality challenges the scientific ideal of objective observation. In the quantum world, there is no such thing as a truly passive observer. Every measurement is an interaction, every observation an intervention. We cannot study the quantum realm without changing it, cannot observe without participating in the creation of what we observe. The double-slit experiment, with its elegant demonstration of the observer effect, stands as one of the most beautiful and disturbing revelations in the history of science. It shows us that reality is far stranger and more wonderful than our everyday experience suggests. The universe is not a clockwork mechanism running independently of observation, but a dynamic, interactive system where consciousness and cosmos dance together in ways we're only beginning to understand. In the end, the observer effect reminds us that we are not merely witnesses to reality, but active participants in its unfolding. Every measurement we make, every question we ask, every experiment we perform helps to weave the tapestry of existence. We've been dancing around something rather unsettling throughout this exploration, and now it's time to face it directly. The double-slit experiment doesn't just suggest that reality is strange or mysterious. It suggests that reality as we know it, as we've always assumed it to be, might not exist at all in the way we think it does. Let's sit with this for a moment. The implications ripple outward like waves from a stone dropped in still water, touching everything we thought we understood about existence itself. Consider what we've discovered. When we're not looking, particles behave as waves of possibility, existing in multiple states simultaneously. They pass through both slits at once, interfering with themselves, creating patterns that speak of their wave-like nature. But the moment we decide to observe, to measure, to know which path they take, the wave function collapses. The particle chooses a path. The interference pattern vanishes. This is more than just a curious laboratory phenomenon. This is reality itself changing based on the act of observation, not just our knowledge of reality, but reality. The philosophical implications are staggering. If particles exist in superposition until observed, what does this mean for the nature of existence itself? Are we living in a universe where things only become real when witnessed? Where the act of consciousness, of awareness, of measurement brings reality into being? Some interpretations of quantum mechanics suggest exactly this. The participatory universe hypothesis proposes that consciousness plays a fundamental role in shaping reality. Not consciousness as some mystical force, but consciousness as an information processing system that collapses wave functions through the act of observation. Think about it this way. Every moment of every day, you're making countless unconscious observations. Your eyes detect photons, your ears register sound waves, your skin feels temperature and pressure. Each of these interactions could be seen as a measurement, a collapse of possibility into actuality. You're not just experiencing reality, you're participating in its creation. This leads us to one of the most profound questions in physics and philosophy. If reality requires observation to become definite, what happens to the parts of the universe that no one is observing? Are distant galaxies existing in superposition until our telescopes peer into the cosmic darkness? Did the universe exist before conscious observers evolved to witness it? The delayed choice quantum eraser experiment pushes this even further into the realm of the extraordinary. In these experiments, scientists can decide whether to observe which path a particle took, even after the particle has already reached its destination. The remarkable finding is that this future decision seems to retroactively determine whether the particle behaved as a wave or a particle in the past. Let that sink in. The choice to observe or not observe can apparently influence events that have already occurred. It's as if the universe maintains a kind of quantum uncertainty about its own past, until that uncertainty is resolved by future measurements. This suggests something even more radical than a universe shaped by consciousness. It suggests a universe where the flow of time itself might be more fluid than we imagine, where cause and effect might not follow the neat linear progression we assume, where the future might reach back to shape the past. Of course, there are other interpretations. The many worlds interpretation sidesteps these paradoxes by suggesting that all possible outcomes actually occur, each in its own parallel universe. When we make a measurement, we're not collapsing possibilities into a single reality. We're simply finding ourselves in one branch of an infinitely branching multiverse. In this view, there's a universe where the particle went through the left slit, another where it went through the right slit, and countless others where it did both simultaneously. We experience only one thread in this vast tapestry of realities, but all threads are equally real. This interpretation preserves the objectivity of reality, but at the cost of multiplying it infinitely. Instead of consciousness creating reality, consciousness selects which reality to experience from an infinite menu of possibilities. Then there's the pilot wave theory, which suggests that particles do have definite positions and velocities at all times, but they're guided by a quantum field that we can't directly observe. In this view, the randomness and uncertainty we observe aren't fundamental features of reality, but simply limitations of our knowledge. Each interpretation grapples with the same fundamental mystery. How do we reconcile the quantum world of possibilities with the classical world of definite outcomes? How do we bridge the gap between the microscopic realm where particles exist in superposition and the macroscopic realm where cats are either alive or dead, never both? The answer might be that there is no bridge, that we live in a universe with two different sets of rules, one for the very small and one for the everyday. The quantum world operates according to the strange logic of superposition and entanglement, while the classical world emerges from the collective behaviour of countless quantum systems. But even this comfortable division is being challenged. Quantum effects have been observed in increasingly large systems. Scientists have created superposition states in molecules, in tiny mechanical oscillators, even in collections of atoms large enough to see with the naked eye. The boundary between the quantum and classical worlds isn't as clear as we once thought. It's more like a gradient, a gradual transition from the strange to the familiar. And as our technology improves, we're pushing that boundary further into the realm of everyday experience. This raises profound questions about the nature of reality at all scales. If quantum mechanics applies to large systems, might there be situations where everyday objects exist in superposition? Could there be circumstances where the classical world itself becomes uncertain, probabilistic, observer-dependent? We're not there yet. The quantum effects that govern particles become vanishingly small in large systems. But the principle remains. Reality at its most fundamental level is not what it seems. It's not a collection of definite objects with definite properties existing independently of observation. It's something far stranger and more wonderful. It's a shimmering web of possibilities, constantly collapsing and reforming through the act of measurement. Now, let's turn to one of the most perplexing aspects of the double-slit experiment, something that has puzzled physicists for nearly a century and continues to challenge our understanding of reality itself. We've seen how particles behave like waves when unobserved, creating interference patterns that seem to defy common sense. We've explored how measurement collapses these possibilities into definite outcomes. But there's another layer to this mystery, one that pushes the boundaries of what we consider possible even further. Picture this scenario. You're conducting the double-slit experiment, but this time you decide to place your detector not right at the slits, but somewhere else entirely. Perhaps you position it just after the screen, or maybe you set up a delayed measurement system. What happens when you choose to observe which slit the photon passed through only after it has already hit the detection screen? Logic would suggest that the photon's path has already been determined by the time it reaches the screen. The interference pattern should already be established, shouldn't it? This is where quantum mechanics takes us into truly bewildering territory. In what's known as the delayed choice experiment, first proposed by physicist John Wheeler and later demonstrated in laboratories around the world, the decision to measure which slit the photon passed through can be made after the photon has already travelled through the apparatus. The extraordinary result is that this delayed choice still determines whether an interference pattern appears or not. It's as if the photon somehow knows retroactively whether it will be observed, and it adjusts its behaviour accordingly. The implications of this are staggering. It suggests that the act of measurement doesn't just affect the present state of a particle, but can somehow influence its past behaviour. The photon's journey through the slits, which we might assume is fixed in history, appears to be malleable based on future observations. This challenges our most basic assumptions about causality and the flow of time itself. Consider what this means for our understanding of reality. If future measurements can influence past events, then the notion of a fixed, unchanging history becomes questionable. The past, at least at the quantum level, might be more fluid than we ever imagined. This doesn't mean we can change macroscopic historical events, but it does suggest that the microscopic foundation of reality operates according to rules that are far stranger than our everyday experience would suggest. Some physicists have proposed that this delayed choice behaviour indicates that quantum systems exist in what might be called a state of temporal superposition. Just as a particle can be in multiple spatial locations simultaneously, perhaps the information about its path through the slits exists in a superposition of being determined and undetermined until the moment of measurement, regardless of when that measurement occurs. This connects to a broader concept in quantum mechanics known as non-locality. Einstein famously called this spooky action at a distance, referring to how quantum particles can influence each other instantaneously across vast immense distances. But the delayed choice experiment suggests something even more mind-bending: spooky action across time. The measurement in the present appears to have a retroactive effect on the particle's behaviour in the past. The delayed choice experiment also raises profound questions about the nature of information itself. In our classical understanding, information about an event is created when the event occurs and then persists through time. But quantum mechanics suggests that information might be more fundamental than we realize. Perhaps information about the particle's path exists in a kind of quantum limbo, neither created nor destroyed, but simply accessed or revealed by the act of measurement. This has led some researchers to propose that reality itself might be informational in nature. Rather than thinking of particles as tiny billiard balls moving through space, we might need to conceive of them as patterns of information that become concrete only when observed. The delayed choice experiment supports this view by showing that the concreteness of a particle's path can be established retroactively. From a practical standpoint, delayed choice experiments have been conducted using increasingly sophisticated setups. Researchers have used quantum random number generators to decide whether to measure the particle's path, ensuring that the choice is truly random and made only after the photon has passed through the slits. The results consistently confirm Wheeler's predictions. The interference pattern appears or disappears based on the delayed choice to measure. These experiments have also been extended to cosmic scales. Some researchers have proposed using light from distant quasars, where the choice of measurement is made billions of years after the light began its journey. Even in these scenarios, the delayed choice effect persists, suggesting that the strangeness of quantum mechanics operates consistently across both microscopic and cosmic scales. The delayed choice experiment also intersects with theories about quantum gravity and the nature of space-time itself. If measurement can influence the past, it raises questions about whether space-time at the quantum level has the same fixed structure we observe in our everyday world. Some theories propose that space-time itself might be emergent from quantum information, and experiments like the delayed choice setup provide clues about how this emergence might work. For many physicists, the delayed choice experiment represents one of the clearest demonstrations that quantum mechanics is not just a convenient mathematical tool, but a fundamental description of reality's strange nature. It shows that the act of observation doesn't just reveal pre-existing properties of particles, but actually participates in determining what those properties are, even retroactively. This has philosophical implications that extend far beyond physics. If the past can be influenced by present choices, what does this mean for concepts like free will and determinism? If reality is fundamentally informational and observation dependent, how do we understand our role as conscious observers in the universe? The delayed choice experiment doesn't answer these questions, but it forces us to confront them with a new level of urgency. The experiment also highlights the inadequacy of our everyday language for describing quantum phenomena. We use words like before and after, cause and effect, but these concepts may not apply in the quantum realm in the way we expect. The delayed choice experiment suggests that quantum events exist in a more complex relationship with time than our classical intuitions can accommodate. As we continue to explore the implications of the double-slit experiment and its variations, we're confronted with a reality that operates according to principles that challenge our deepest assumptions about the nature of existence. The delayed choice experiment is perhaps the most dramatic illustration of this, showing us that even our understanding of time and causality may need to be reconsidered in light of quantum mechanics. The mystery deepens when we consider that these quantum effects somehow give rise to the classical world we experience every day. How does a universe built on such strange quantum foundations produce the stable, predictable reality we navigate? But perhaps the most radical implication of the double-slit experiment isn't what it tells us about particles or waves or even measurement itself. Perhaps it's what it whispers about the nature of reality as a whole. You see, if observation can influence quantum events, and if quantum events form the foundation of everything we call real, then we might be living in a universe that is far more participatory than we ever imagined. Think about it quietly for a moment. Every measurement, every observation, every conscious act of looking might be a kind of collaboration with the cosmos. Not in some mystical sense, but in a deeply physical one. The universe, it seems, doesn't simply exist in some fixed state waiting for us to discover it. Instead, it appears to be constantly creating itself through the very act of being observed. This leads us to one of the most profound questions in all of science. What exactly constitutes an observation? Is it the conscious awareness of a human mind, the mechanical clicking of a detector, the entanglement of information with the environment? The answer, frustratingly and beautifully, remains elusive. But what we do know is that the line between observer and observed, between the measurer and the measured, is far blurrier than our everyday experience suggests. Consider the implications for how we understand ourselves. If consciousness plays any role in the collapse of quantum superpositions, then we are not merely passive witnesses to reality. We are active participants in its ongoing creation. Every moment of awareness, every decision to look or not look, every measurement we make might be a small act of cosmic collaboration. But even if consciousness itself isn't the key, even if observation is simply about information transfer or environmental interaction, the message remains startling. Reality appears to be fundamentally relational. Things don't simply exist in isolation. They exist through their interactions, their connections, their entanglements with everything else. This relational view of reality echoes through other areas of physics as well. In Einstein's relativity, space and time are not absolute backdrops, but dynamic relationships between objects and events. In quantum field theory, particles are not little billiard balls, but excitations in underlying fields that permeate all of space. Cannot be answered without reference to how we choose to look at it. The experiment also challenges our intuitions about locality, the idea that objects can only be influenced by their immediate surroundings. Through quantum entanglement, particles that have interacted can remain connected across vast distances. Change the state of one, and its entangled partner responds instantaneously, regardless of the space between them. Einstein famously called this spooky action at a distance, but experiments have repeatedly confirmed that this spookiness is real. What's more, some interpretations of quantum mechanics suggest that this non-locality might be fundamental to how reality works. The universe might be more like a vast web of interconnected relationships than a collection of separate objects bumping into each other. In this view, the double-slit experiment isn't just showing us something strange about particles, it's revealing the deeply interconnected nature of existence itself. And then there's the question of time. In some delayed choice experiments, the decision about how to measure a particle seems to retroactively determine its history. It's as if the future can reach back and influence the past, at least at the quantum level. This suggests that our usual understanding of causality, where causes precede effects in a neat, linear fashion, might be incomplete. Perhaps time itself is more fluid than we imagine. Perhaps the universe is not a mechanical clockwork where the future is determined by the past, but something more like a vast conversation between all possible moments, with each observation helping to weave the threads of what becomes real. The double-slit experiment, in its quiet way, invites us to consider that reality might be far stranger and more wonderful than our everyday experience suggests. It hints at a universe where observation matters, where relationships are fundamental, where the boundary between mind and matter is mysteriously permeable, and where the act of knowing might be inseparable from the act of being. This doesn't mean we should abandon reason or embrace mysticism. Rather, it suggests that reason itself might lead us to conclusions that feel mystical, that the universe revealed by careful scientific investigation might be more magical than any fairy tale. The double-slit experiment, with its simple setup and profound implications, reminds us that we live in a cosmos where the impossible happens every day, where mystery is not the absence of knowledge, but its deepest expression. As we drift toward the end of our journey through this quantum wonderland, we're left with questions that are both humbling and exhilarating. What does it mean to exist in a universe where observation shapes reality? How do we live with the knowledge that the very act of knowing might be an act of creation? So here we are at the end of our journey through the double-slit experiment, standing at the edge of understanding and peering into the vast mystery that remains. We've watched photons dance through both slits at once, seen reality collapse under observation, and witnessed the universe revealing itself as something far stranger and more participatory than we ever imagined. Yet perhaps the most remarkable discovery isn't what the experiment tells us about particles or waves, but what it whispers about the nature of existence itself. The double-slit experiment doesn't just challenge our understanding of physics, it challenges our understanding of what it means to be. In a universe where observation shapes reality, where information travels backward through time, where the very act of knowing changes what is known, we find ourselves not as passive observers watching a cosmic theatre, but as active participants in an ongoing creation. Reality, it seems, is not a fixed stage upon which we perform, but a collaborative dance between consciousness and cosmos, observer and observed, question and answer. Think about what this means for your own existence. Every moment of awareness, every act of attention, every choice to look or not to look becomes a creative act. You are not simply experiencing reality, you are helping to weave it into being. The universe doesn't just happen to you, it happens with you, through you, as you. The boundary between self and world, between mind and matter, becomes as fluid and mysterious as the wave-particle duality itself. This participatory universe suggests something profound about consciousness and its role in the fabric of existence. Perhaps consciousness isn't just an emergent property of complex matter, but something more fundamental, woven into the very structure of reality. The observer effect hints that awareness and physical reality are not separate phenomena, but aspects of a deeper unity, like two sides of a single coin, spinning through dimensions we can barely comprehend. The implications ripple outward into every corner of human experience. If reality is indeed participatory, then our thoughts, intentions, and observations carry weight beyond what we might have imagined. The quality of our attention, the nature of our questions, the depth of our wonder, all become part of the cosmic conversation. We are not just studying the universe, we are part of its ongoing self-discovery. This doesn't mean we can simply think our way to any reality we choose. The universe has its own grammar, its own rules, its own mysterious logic. But it does suggest that the relationship between mind and world is far more intimate than classical physics ever dared to dream. We exist in a universe that seems to know itself through our knowing, that becomes real through our observations, that perhaps even dreams itself into existence through the countless acts of consciousness scattered across space and time. The double-slit experiment also reveals something beautiful about the nature of mystery itself. For all our sophisticated equipment and elegant theories, for all our delayed choice experiments and quantum erasers, the experiment continues to perplex and amaze. It reminds us that mystery is not simply the absence of knowledge, but the presence of something deeper, something that invites us into relationship rather than demanding conquest. This is the gift of true mystery. It transforms us in the encountering. We don't solve the double-slit experiment so much as we allow it to reshape our understanding of what it means to exist in a universe far more magical and interconnected than we ever suspected. It invites us to embrace uncertainty, not as a failure of knowledge, but as an opening into wonder, a doorway into the deep creative mystery of existence itself. The experiment teaches us that reality is not a collection of facts to be discovered, but a living process to be participated in. It shows us a universe that is not mechanical, but organic, not predetermined, but creative, not separate from consciousness, but intimately woven together with it. This is a universe where the future influences the past, where possibilities exist in superposition until crystallized by observation, where the very act of questioning becomes part of the answer. Perhaps most beautifully, the double-slit experiment reveals that we live in a universe that responds to attention, that rewards curiosity, that opens itself to those who approach with genuine wonder. It suggests that the cosmos is not indifferent to our presence, but somehow enriched by it, not diminished by our questions, but enlivened by them. not threatened by our explorations, but fulfilled through them. In the end, the double slit experiment stands as a perfect metaphor for the human condition itself. We are being suspended between certainty and uncertainty, between knowing and not knowing, between the wave of possibility and the particle of actuality. We exist in the space between question and answer, in the moment between observation and collapse, in the eternal dance between what is and what might be. The experiment reminds us that we are not separate from the mystery we seek to understand, but part of it, expressions of it, participants in its ongoing unfoldment. We are the universe becoming conscious of itself, reality awakening to its own nature, existence exploring its own possibilities through the gift of awareness. And so we return to where we began, to the simple setup of 2 slits and a beam of light, but now we see it with new eyes. We see not just an experiment, but a revelation, not just a puzzle, but an invitation, not just a demonstration of quantum mechanics, but a glimpse into the creative heart of existence itself. The double slit experiment changes reality because it reveals that reality is always changing, always becoming, always dancing on the edge of the possible. We are part of that dance, participants in that becoming, collaborators in that endless creative unfolding. The universe doesn't just contain consciousness, it expresses itself through consciousness, knows itself through consciousness, perhaps even dreams itself into existence through the countless acts of awareness that sparkle like stars across the vast night of possibility. This is the quiet revolution of the double slit experiment. Not just a new understanding of physics, but a new way of being in the world. We are not strangers in a strange land, but intimately woven into the fabric of existence itself. Not observers of reality, but participants in its ongoing creation. Not separate from the mystery, but expressions of it. Living embodiments of the universe's endless capacity for wonder, discovery, and transformation. The experiment that changes reality changes us as well, inviting us to step more fully into our role as conscious participants in the cosmic dance, as co-creators in the ongoing story of existence, as expressions of the universe's eternal quest to know itself ever more deeply, ever more completely, ever more lovingly. In discovering the participatory nature of reality, we discover something profound about ourselves. We are not just in the universe, we are the universe, awakening to its own infinite mystery and endless creative potential.